Okay, we should be live. Checking my sound to make sure we are using the right microphone. Yeah, that sounds correct. Okay, so we are using AI, obviously, as you can tell, but there is a human in the loop. So you're more than welcome to ask questions. Everything we do eventually appears on this website, so go check it out. That's a usual spiel. So yesterday we asked ChatGPT about the FNIRS, functional near infrared spectroscopy. It gave us did a deep dive, 6 minutes, which is gazillion. Which is a very long time in machine time. It's like 6 years or something. So it gave us this, it did all the research as a good, whatever it would be, I guess, the level of a master's student. I'm curious about the scenery. What? It's actually found some image. Yeah, we're actually able to replicate it, not taking the source just from the description of the image. Yeah, Gemini is a mixed bag. Yeah, it was able to generate this video. The video, yeah, the video is there. Okay, and the last time, we had the video going, so we gave all the deep dive, the deep research text to Notebook LM. So let's play that quickly. We can actually interact with it as we go, so we might do that.
Welcome to the Deep Dive. Today we're tackling a really interesting challenge in brain science. How do we actually study minds in action when, people aren't stuck inside a huge scanner or wired up in some silent lab?
Right, like how do you see what the brain's doing when someone's learning in a classroom or an athlete's performing?
Or even a baby interacting with their parent. I saw mention of astronauts too.
Exactly. For so long, our best tools kind of tied us down to these really controlled settings.
Yeah.
But we've got this source overview here on a technology that's really starting to break those chains. It's called functional near infrared spectroscopy, FNIRS for
And NIS, okay.
And this deep dive, well, it's all about getting to grips with how FNIRS works. It's a clever trick for seeing brain activity.
Yeah, that's the thing I keep forgetting, that if you change the window size or something, it actually stops playing. That's a bit annoying.
Welcome to the Deep Dive. Today we're tackling a really interesting
Okay, there
challenge
is a
in
human
brain
in the loop,
science.
so
How do we actually
do ask
study
questions.
minds in action when, people aren't stuck inside a huge scanner or wired up in some silent lab?
Right, like how do you see what the brain's doing when someone's learning in a classroom or an athlete's performing?
Or even a baby interacting with their parent. I saw mention of astronauts too.
Exactly. For so long, our best tools kind of tied us down to these really controlled settings.
Yeah.
But we've got this source overview here on a technology that's really starting to break those chains. It's called functional near infrared spectroscopy, FNIRS for
And NIS, okay.
And this deep dive, well, it's all about getting to grips with how FNIRS works. It's a clever trick for seeing brain activity.
And I guess where its limits are.
Definitely, where it hits the law, but also, crucially, discovering these unique, sometimes kind of surprising places it's popping up.
So we're talking babies, maybe mountain peaks, even space simulations.
You got it. It's about understanding the tool that lets us finally peek at the brain, sort of in its natural habitat.
Okay.
Oh, hey there, how can we help?
Okay, can you actually get to the point and cut out the fluff, go into the technical details and the data sets available for this type of research?
Absolutely, I understand. Let's dive straight into the core
You
mechanism.
want to know how FNIRs actually works, the nuts and bolts, right?
So FNIRs uses near-infrared light in the 700 to 900 nanometer range.
Near infrared?
Yes, and this light can safely pass through skin, skull, and brain tissue.
Okay, like shining the light through your hand.
A similar principle, we shine this specific light into the scalp,
Right.
detectors a few centimeters away, then measure the scattered light that comes back out.
And the key is what happens to that light.
Exactly. It's the absorption by hemoglobin in your blood.
The stuff that carries oxygen. Precisely. Oxygenated HBO and deoxygenated HBr, hemoglobin absorb this light differently.
So the oxygen level changes how much light gets through.
Exactly. By measuring these changes in light intensity,
And doing some calculations.
using the modified Beer-Lambert law, we can estimate changes in HBO and HBr concentrations.
And this all happens with portable gear. Yes, relatively small light sources and photodetectors.
In a cap or headband.
Typically, sources and detectors are spaced a few centimeters apart.
And the light's path isn't straight.
It follows a banana shape, going into the cortex and back to the detector.
Okay, got it. You need multiple light wavelengths too.
Yes, at least two, because HPO and HBr absorb different wavelengths differently.
So you can track both.
Precisely. But remember, we're measuring changes over time, an indirect measure.
Indirect, like fMRI and blood flow.
You got it. It's the same neurovascular coupling principle.
Neurons firing means more oxygen needed.
Exactly. Blood flow increases, overshooting with oxygenated blood.
And that's what FNIRS detects.
Right. It's not direct neuron firing like EEG.
It's the slower blood flow change.
Yes, lagging by a second or two, peaking over several more.
So even with fast sampling,
The underlying biological signal is slow, a trade-off for portability.
most FNIR systems just measure light intensity.
Yes, continuous wave FNIRS is the most common, simpler, and more portable.
But there are more advanced types.
Frequency domain and time domain FNIRS offering more potential information but less portability.
Okay, sticking with the common type, optos in a cap create channels,
Yes, each source detector pair is a channel,
measuring a volume of brain tissue. How deep?
typically just the cerebral cortex, maybe 1 to 2 centimeters deep.
So not very deep.
No, deeper structures are out of reach for FNRS.
The signal itself isn't very strong either.
Very tiny changes in light, meaning noisy raw data.
Lots of processing needed then.
Filtering, accounting for physiological noise, and crucially, motion artifacts.
Movement is a big challenge.
Yes, even slight shifts can swamp the brain signal.
How do you handle that?
Careful setup and techniques like short separation detectors to measure and regress out scalp blood flow noise.
Trying to isolate the real brain activity.
Exactly, looking for that HBO increase and HBr decrease pattern.
Okay, so shallow depth, limited resolution, scalp contamination, hair skin issues, and motion are key limitations.
Precisely. But that portability allows us to study the brain outside the lab.
Which brings us to the datasets. Where can researchers find FNIRS data?
The field is moving towards open data sharing. There isn't one central repository yet, like OpenNeuro for fMRI, but it is starting to accept FNIRS data.
So where should we look?
There's a great community-maintained list, often on GitHub, that compiles links to publicly available FNIRS datasets on various platforms.
Like what kind of data is available?
You can find cognitive task data from adults, like that speech perception study we mentioned. Neuroergonomics data, including that NASA astronaut study, though access might be by request.
Interesting.
Multimodal artifact datasets with simultaneous FNIS and TG are available on PhysioNet.
Useful for methods development.
Exactly. You can also find data on cognitive workload and resting state connectivity.
And BCI data as well.
Yes, datasets from mental arithmetic and motor imagery tasks for BCI research.
What about developmental or clinical data?
There are datasets from children with ADHD and adults undergoing neurofeedback, though access might be controlled for sensitive data.
So a good range of data is becoming available.
Yes, reflecting many research areas, this open data is invaluable for learning, testing methods, and advancing the field.
It sounds like a great resource for researchers.
Absolutely, though always check the specifics of each dataset.
Okay, that gives us a much clearer picture of the technical side and the available data.
So, with this understanding of how FNIRS works and the data available, we can appreciate its unique contributions to brain research.
Definitely. It's about getting insights into the brain in real-world scenarios.
And the growing availability of data and analysis tools is making this field even more exciting.
It really does. It fills a crucial gap in how we study the mind.
That concludes our deep dive into FNIRS for today.
Thanks for joining us on the deep dive. We hope you found this illuminating.
We appreciate your engagement and curiosity. Until next time.
Okay, sorry for that. I thought it will actually talk for half an hour. So that's interesting because when you interact with the thing, the original thing meant to be 30 minutes, but then I said, cut out the fluff, and it's actually moved forward within the conversation. So that's interesting. Close that. So eventually everything goes onto the side. Yeah, I'm not sure if we surprisingly still using Visual Studio Code. I don't know why. I don't know why. Well, we were not able to actually replace it with anything else. And yeah, so we have, and this thing. So it's actually stuffed up our thing, because yesterday we were making a lot of changes to it, and just removed all the code, which is not fun. It didn't actually save anything, so I didn't know you have to save stuff. I mean, you can make a local copy of the app, which is fine, but I didn't actually know you have to do it. Yeah, you can upload the image to it. Don't know if will it be able to recover everything we did. Don't think so. I don't think so. Yeah, we got it working yesterday. I'm wondering, just for the sake of trying things out. Just drop images? No. So yesterday we had it, we developed it further, and it didn't save any of the changes. Can you explain what happened there? And yeah, I think there's no point asking questions about yourself, about how you operate. But then we have this image of what we got up to yesterday. Can you, by any chance, restore it to upgrade it to that position so it looks like, so everything you see in the image actually works in the web application? Don't think it will able to do it, because it didn't actually save a code or anything. Yeah, I'd like to try the notebook elements again, So we can do either 30 minutes of it, well, the two hosts, whatever, talking to one another, or you can have interactive mode where you can interject. That doesn't seem to work. Is anything loading? It wasn't just the UI. We had we had data. Yeah, get rid of it. Yeah, really don't understand how it works. So I'm wondering if it's just good for prototyping, or we can actually replace Visual Studio Code with this and just develop in the browser. Not sure. So in Visual Studio Code, we have GitHub Copilot. So if we had an image, and the prompt, we don't have the prompt. Version was a thing. It didn't save any of the work we did. I'm not sure how that. Right, there's an actual save button. It's actually quite surprising. I didn't expect it. Don't get it. I don't get it.
Welcome to the Deep Dive. Today we're tackling a really interesting challenge in brain science. How do we actually study minds in action when, people aren't stuck inside a huge scanner or wired up in some silent lab?
Right, like how do you see what the brain's doing when someone's learning in a classroom or an athlete's performing?
Or even a baby interacting with their parent. I saw mention of astronauts too.
Exactly. For so long, our best tools kind of tied us down to these really controlled settings.
Yeah.
But we've got this source overview here on a technology that's really starting to break those chains. It's called functional near-infrared spectroscopy, FNIRS for
And NIS, okay.
and this deep dive, well, it's all about getting to grips with how FNIRS works. It's a clever trick for seeing brain activity.
And I guess where its limits are.
Definitely, where it hits the law, but also, crucially, discovering these unique, sometimes kind of surprising places it's popping up.
So we're talking babies, maybe mountain peaks, even space simulations.
You got it. It's about understanding the tool that lets us finally peek at the brain, sort of in its natural habitat.
Okay, let's do it. Let's unpack the science and see where it fits.
So, first things first, how does it actually let us study the brain in the wild, so to speak?
Yeah, what's the principle?
Well, at its core, FNIRS uses a pretty simple idea. Light, it's non-invasive, and it uses near-infrared light.
Near infrared.
Yeah, that's in the 700 to 900 nanometer range. And the key thing is, this type of light can pass safely through skin, bone, and importantly, brain tissue.
Okay, like how you can shine a bright light through your fingers and sort of see the red glow. Is it like that?
It's kind of based on a similar principle, yeah. You shine this specific light into the scalp,
Right.
and then you have detectors placed a few centimeters away that measure the light that scatters back out.
And the trick is in that scattering.
The trick is in the absorption. See, the hemoglobin in your blood, the molecule that carries oxygen,
Right.
it absorbs this near-infrared light differently depending on whether it's carrying oxygen or not. So oxygenated hemoglobin, HbO, and deoxygenated hemoglobin, HbR, have different light absorption profiles.
Ah, okay. So the amount of oxygen changes how much light gets through.
Precisely. By measuring how the light intensity changes between the source and the detector, and using a physics principle called the modified Beer-Lambert law,
Okay.
you can actually estimate how the concentrations of HbO and HbR are changing in the tissue the light passed through.
And the gear for this, it's small enough to be portable?
Yeah, relatively speaking, you use small light sources, usually LEDs or maybe low power lasers and these little photodetectors.
And you stick them on the head?
Pretty much. They're typically arranged in a cap or maybe a flexible headband that fits onto the person's head. The sources and detectors are spaced a few centimeters apart, usually around 3 centimeters.
And the light travels. How does it go straight through?
Not exactly straight. It follows more of a banana-shaped path, arcing down through the scalp and skull into the top layer of the brain tissue and then back up towards the detector.
Okay, got it.
And the really crucial bit here is that you need to use at least 2 different wavelengths of this near-infrared light from each source.
Why 2?
Because HPO and HPR absorb light differently at different wavelengths. By using 2 or more, the system can mathematically separate out their signals.
So you can track both oxygenated and deoxygenated blood changes.
Exactly. But it's important to remember what fMRS is measuring is the change in these concentrations over time. It's an indirect measure of brain activity.
Indirect. Okay, that sounds familiar. That makes me think of fMRI and blood flow.
You nailed it. It relies on the exact same principle. Neurovascular coupling. It's the foundation of the bold signal in fMRI too.
So when neurons fire up in a brain area,
They need more energy, more oxygen, so the body responds by increasing blood flow to that specific spot. It actually overshoots, delivering more oxygenated blood than is immediately used.
right.
And this rush of fresh blood leads to an increase in the local concentration of HPO, the oxygenated stuff, and usually a dip in HBr, the deoxygenated stuff. That's the signal FNIRS picks up.
So just to be clear, you're not directly seeing the neurons firing like you might with, say, EEG.
Not at all, no. You're seeing the downstream effect, that relatively slow change in blood flow, the hemodynamic response.
How slow are we talking?
Well, the blood flow change lags behind the actual neural activity by maybe a second or two, and then it takes several more seconds to reach its peak.
Okay.
So even though the FNRS device itself might be sampling data quite quickly, maybe tens of times per second.
The thing it's measuring is slow.
Exactly. The biological signal itself is inherently slow. That's a fundamental trade-off. You gain portability, but you lose that millisecond precision you get with techniques like EEG or...
Welcome to the deep dive. Today we're
Okay, that's super annoying. I just changed the size of the window and the chat just reset itself. Hopefully they fix it sometime soon. Don't know where we were, because the interactive mode beta, it's like has this weird hover screen which I don't like. But anyhow, okay, so we didn't. Yeah, we're not having much luck with AI Studio. I didn't realize you actually have to save changes. I thought they will be saved for you. as you go through the chat. Okay, so we have a bunch of prompts. So we have an fmis function. We essentially redoing this web application here. We'll do edits with Copilot. We'll have a oops. We'll have another info text file. This will be essentially all our prompts. All our prompts, and we have two so far. So we have an interactive web application. Should we turn it into one prompt? Can we turn the last two responses into one prompt? This will be instructions for a senior web developer to do coding. Don't include any code in your response. And we would like the developer to generate just 4 files. So the JavaScript, JSON, HTML, CSS. The CSS actually can be just inside the HTML. Well, the thing is that we have another external CSS file for the whole project. So any unique components to this web application should be just in the HTML, not in a separate section, but where the component is actually defined within the HTML. Hope that makes sense. Now, so we want to combine the last two prompts. We want the web application to load a synthetic data file as we open the web application the first time. And let's see what it does. Okay, I'm not gonna read this because it's not suitable for speech, for text to speech. Okay, so can we generate the continuous, like it meant the instructions meant to be standalone. Keep in mind that the developer that we have is a senior developer. So just essentially potentially ask questions, don't actually tell them what to do. But also we want as little external libraries as possible. We essentially just want charting library, so visualization library, potentially math.js, and that's pretty much it. Now, potentially, we would like to have Python code that will generate the synthetic data only once. I'm thinking about it. Maybe not. Maybe not. No, just rely on JavaScript. Yes, so no, so we're not generating the data offline. The whole thing will just try to have it all in the beginning of the standalone instructions. Can we also have a continuous text overview of what this application will be doing and what is it all about? This actually looks continuous text. Let's actually read this quickly.
This interactive web application is a lightweight, standalone tool for exploring and analyzing synthetic FNIR functional near-infrared spectroscopy data entirely in the browser. It is built using vanilla JavaScript, HTML, and a single static JSON file that emulates a real-world continuous wave FNIRS recording. The interface should support interactive signal inspection, visual overlays of hemoglobin concentration changes, event alignment, and a minimal topographical view of source detector channels. The application should require no backend and run fully offline. The only libraries to consider are a small, performance-efficient charting library like Chart.js or uplot, and optionally Math.js for signal operations. Everything else should be implemented in native JavaScript. When the page loads, the app should automatically read a bundled data.json file and immediately render the default visualizations, simulating a scenario where a researcher opens a pre-recorded dataset for inspection. The synthetic dataset must be realistic. It should simulate oscillating hemodynamic signals, HBO and HBR, include embedded task-related events, and contain multiple spatially distributed channels that reflect a plausible optode montage. The goal is to provide both a technical testbed for development and a functional demonstration of FNAR's analytics UX. Would it make sense to have the JSON include only oxy and deoxyhemoglobin traces per channel? Or should the raw light intensities and physiological artifacts also be simulated? What level of realism are you expecting in the physiological noise? Does it need to separate cardiac, respiratory, and Mayer wave components with appropriate frequency content? For events, are you assuming only stimulus-type markers, or would conditions with variable timing and duration be required to simulate real task paradigms? The UI is composed of 3 functional regions: a control panel for filtering and navigating channels or events, a central visualization canvas that switches between time series and topographical views, and a right-hand interaction module for adjusting plot parameters and exporting data. Are you envisioning a full GUI, or would keyboard shortcuts and minimal UI elements be preferred for a more data-centric experience? The charting component must handle real-time zooming, panning, and signal overlays across dozens of channels. Would something lightweight like uplot suffice, or should you plan for more modular plotting, perhaps writing your own layer on top of Canvas or SVG? Are multi-channel plots synchronized on a shared time axis, or would per-channel time cursors be useful? For the HTML structure, are you expecting a declarative layout that adapts to screen size with flex grid, or do you want fixed panel dimensions to maintain predictability across environments? Since the CSS must not pollute the global style sheet, should all component-specific styling be embedded in line using scoped style tags adjacent to the components? Or would a JS-driven class injection pattern be acceptable? As for loading the JSON file, do you prefer a blocking load during page initialization to ensure no visual glitch, or a deferred async fetch with a loading screen or spinner? Should malformed or missing fields in the JSON trigger console warnings, user-facing alerts, or both? Finally, what would you expect from the export functionality? Just raw JSON dumps of selected signals, or also rendered SVG PNG plots with annotations? And if future real datasets are swapped in place of the synthetic one, should this tool already handle large file optimizations, e.g. downsampling, chunk loading, or is that outside the current scope?
Okay, let's let's keep it more simple. Okay, forget the export for now. Can we forget the export functionality? And can we also remove the loading new dataset? We're just working with the synthetic JSON file that we'll be generating. Can we just yeah, we'll do it in multiple steps. Can we focus on the synthetic data JSON file? Can we have instructions for a senior JSON data set developer to actually generate the file? Let's do one thing at a time. One thing at a time. Okay, shall we try the all new Claude Sonnet 4? Can you give a continuous text overview for this synthetic data, and also mention, would it be optimized for having some automated playing of the data? If you know what I mean, can you explain, elaborate on that?
This synthetic FNIRS dataset is a handcrafted simulation of a real-world brain imaging session, structured to reflect the standard output of a continuous wave FNIRS system. It represents a simplified but believable recording scenario. A single subject wearing a multi-channel optode cap during a short experimental task involving 2 to 3 stimulus blocks. The goal is to produce a fully self-contained JSON file that mimics the temporal, spatial, and physiological dynamics observed in actual FNIRS recordings, without the complexity or noise that comes with real clinical or research data. The dataset includes metadata describing the session, a map of source detector geometry, an array of functional channels, each capturing either oxyhemoglobin or deoxyhemoglobin concentration, and a precise time series of signal data sampled uniformly over a short duration. Hemodynamic responses are embedded at defined event time points, creating realistic, localized bumps in signal amplitude consistent with neural activation. Physiological noise is layered in, cardiac oscillations around 1 Hz, slower respiratory fluctuations and very low frequency drifts to give the signal a more natural rhythm and to test how the front end handles background variability. Each channel delivers a continuous stream of data, with HBO and HBR typically having mirrored but non-identical waveforms, which is critical for visual clarity and realism. Events are time-stamped cleanly and aligned with signal changes, offering natural anchors for dynamic interactions like event highlighting, alignment, or averaging. This file is explicitly optimized for automated playback or time-based signal navigation. Because the sampling rate is fixed and relatively low, e.g. 10 Hz, the time series arrays are predictable and evenly spaced, ideal for looping, scrubbing, or animating through the data at runtime. A front end can easily map each sample index to a time offset, enabling smooth play-pause behavior, timeline animations, or real-time marker syncing without needing interpolation. Signals are designed to evolve slowly and predictably enough that even basic animation timing functions, like request animation frame or a JS timer loop, can simulate the flow of data in real time, mimicking what you might see on a live NERS system. In short, this dataset is a sandbox. It's clean, consistent, and optimized for deterministic loading and smooth interactive visualization. You're not debugging strange edge cases in physiology. You're focused on UI interactivity and performance. It's a scaffold for building out exploratory tools. Zooming into a signal, highlighting task-related changes, toggling between hemoglobin types, or linking spatial positions to time series. And since everything is synthetic, you're free to scale complexity up or down, more channels, longer durations, different event types, without worrying about consent, privacy, or institutional constraints.
Yeah, not worrying about institutional consent sounds great, but yeah, why are we going for a 1020 simulation? I mean, is it normal that FNIRS has a 1020 montage? Can you explain this in plain language? Continuous text? Actually generating the data as labels and everything. What's the sampling rate? So we have location. Wavelets are always the same, so what's the point of having them? Yeah, we have a similar EEG montage as used in EEG, but this is
The
FNIRS.
reason you often see FNIRS datasets referencing the 1020 system, or some simulation of it, is because it's a convenient, widely understood way to organize sensors on the human head. The 1020 system comes from EEG, not FNIRS, and it's essentially a map that tells you where to place electrodes based on consistent anatomical landmarks like the nose, ears, and the top of the skull. Over time, this system became a kind of common language across brain imaging, not just EEG, because it allows researchers to say FP1 or TSICT and immediately know what general part of the brain they're talking about. Now, FNIRS doesn't require you to use the 10 to 20 system, and many high-density or custom setups don't. But when you're building a synthetic dataset or just trying to keep things interpretable, it makes sense to borrow the structure. It gives you something familiar. Instead of inventing a coordinate system from scratch, you can position your synthetic sources and detectors roughly where the 10 to 20 points would fall. This helps in a few ways. It anchors your synthetic channels to meaningful brain regions. It makes it easier to describe or visualize what's being measured. And it keeps your test data compatible with front-end tools that expect some kind of head model or topographic mapping. In practical terms, you're not locked into real anatomical accuracy. You're not building a detailed 3D model of sulci and gyri. You're placing a few optodedes across frontal and temporal regions and calling them FP1, F3, or T7, so that later on, when a user clicks a channel labeled F3T7, they at least know this represents something on the left frontotemporal cortex. It gives your synthetic signals a pseudo-physiological plausibility without needing MRI scans or digitized head shapes. So to answer the question directly, no, FNIRS doesn't have to follow the 10 to 20 system. But when you're simulating data, especially for building tools or testing UI behavior, it's a practical and widely adopted convention that helps keep things organized, interpretable, and interoperable.
Okay, but for simulation purposes, how many channels would be enough? Can you make a decision? And what montage? So how many, essentially out of the 1020, normally, which locations are used for FNIRS recordings? Also, can you comment on the fact that is it even possible to do a full 1020 considering you have essentially two devices on the head, like the transmitter receiver? Can you explain that in continuous text? To generate the channel 10 again. We already have an ID. What are you doing? What? Generated events. Okay, we'll have to accept it. Okay, so is it doing like the 10? Are we just simulating 10 channels? Is that what you suggested? Okay, we have HBO, HBR. Okay, so it seems to know what is it doing. I think we have an expert viewing this, would like your input. Yeah, we'll continue with the development. Okay, can you also generate the instructions for all the JavaScript required? So we have the data as you suggesting. We will accept that. Hey, can you generate the instructions for a senior developer, a JavaScript developer, to do the rest of the web application? So we need to generate a HTML with CSS in it, with styling in it, and also the JavaScript, obviously. But do not generate any code in your response. I need it as a standalone prompt as well, assuming we already have the data JSON file. And we'll read the previous response quickly.
For simulation purposes, 10 channels is a very reasonable and practical number. It gives you enough spatial coverage to demonstrate signal dynamics across different parts of the cortex without overwhelming the visual layout or the browser rendering. This number also reflects the kind of channel density seen in many real-world FNIRS studies, especially those using low to mid-density setups. You're not aiming to recreate a clinical-grade optical tomography scan. You're aiming to simulate a plausible, interpretable dataset that behaves like something you'd see in a focused cognitive experiment. Now, when it comes to the 1020 system and how it applies to FNIRS, things get a bit more nuanced. The 1020 system includes about 21 electrode positions by default, and it can be expanded into 10 to 10 or 10.5 versions for higher spatial resolution. But FNIRS doesn't use these positions in exactly the same way EEG does. Instead of placing sensors directly on those points, FNIRS uses optodes, light sources and detectors, placed on the scalp, and the channels are the regions in between those pairs where light travels.
Okay, oops, wrong button. Meant to copy this. Okay, so I have supposedly a template. a template for the JavaScript. We need to update the index HTML because currently it's just a template for the website. It doesn't have the necessary components. We do have an app.js. Let's do Claude 3.7, meant to be better at coding. Okay, we just had to add the chat.js, did we? Right, well, that's a problem. The app.js, yeah, should have fixed it myself, but relying too much on AI. Yeah, we will accept that. Okay, so the app.js was loaded. Loaded okay, so it seemed to work in general. Let's do Claude Sonnet 4. Okay, so we have all the files, 5 files so far. JavaScript, JSON, HTML should have the CSS in it. Okay, inline CSS sounds good. Yeah, we need to define a sampling rate. Optional enhancement only if time permits. Okay, 2D head layout. Ooh. Okay, let's use this as a single shot prompt with Claude Sonnet 4. So we are in the right folder. We have all the templates for the application. Suppose it's doing 300 seconds of FNIS data synthetic. Scene 01 is the subject ID. We have channels. And we have the data displaying, the synthetic data displaying, but yeah, obviously we need to improve the styling for the page. Okay, so I have the app. Can select all channels, deselect all channels, select a specific channel. I do HBO oxyhemoglobin and deoxyhemoglobin. So oxygenation and deoxygenation. Okay, the play. Is there meant to be a cognitive task in there? Was there meant to be cognitive task? Wait, why do we have... Yeah, it's meant to be resetting somehow. So we have then... Yeah, we need to explain. Okay, so this is Claude Sonnet 4. It is quite impressive. It is quite impressive. So we don't have to look at the code, do we? No. Free panel. Okay, this is what the developer made for us. Can you explain in detail the image, the user interface, and what each part is, and how would you improve it? can we use like GPT-4 or something to add the README? Want a README file, and we want instructions and overview below the page. Actually, I had a good prompt for that somewhere. I have all these live prompts. Should be able to just add the file to the project. Why did it assume MIT last? I don't care. But it's interesting that it makes that assumption. Okay, insert it into a new file. What on earth? What? How did that happen? Hey, can you just insert this README MD into the project folder?
readme.md. Insert the readme file into the project. #FNI.
Okay, can you do it quietly? I was just regenerating it in the chat. And it's meant to be the editing bit. It's bizarre. Okay, create file. Yeah, that was easy, but had to know where to click, and then insert. Okay. Hey, can you turn it into continuous text summary for the whole web application? No, let's just do text summary for the image. Yeah, the play is weird. Why does session start as we're only showing 35 seconds.
This interface is a well-structured and functional first version of a browser-based FNRS visualization tool. It's clearly laid out with a 3-panel design. a left sidebar for selecting channels and signal types, a central area for visualizing time series data, and a right sidebar showing metadata and control options. The dataset it's visualizing is synthetic and meant to simulate a real FNIRS session using a 10-channel setup with hemoglobin signal traces and timestamped task events. The left panel allows the user to toggle specific FNARS channels like FP1F3 or F8T8, each corresponding to a source detector pair, and to filter signal types between oxyhemoglobin HBO and deoxyhemoglobin HBr, clearly color-coded red and blue respectively. It also lists events such as task onset or rest period, giving both the time and the type of cognitive state associated with it. These events are designed to be synchronized with changes in the plotted signal data. The central visualization area displays time series traces for selected channels with separate lines for HBO and HBr concentrations. A vertical line tracks the current time in the playback, and a legend at the top identifies the visible signals. The chart includes axis labels for time and concentration, and the signal data looks cleanly rendered, suggesting the charting library is well integrated. Below the plot, there's a playback control bar with a play-pause toggle, a live time readout, and a speed selector, offering real-time navigation through the dataset. On the right, a static panel provides context for the dataset, showing metadata like subject ID, sampling rate, duration, and system name. It also displays the current time, how many channels are active, and what event, if any, is currently overlapping with the timeline. There are also utility buttons for resetting the zoom and selecting or deselecting all channels at once. Overall, the design works well for exploring a synthetic FNIRS dataset. But while the core features are all in place, there's still room for improvement. The layout could benefit from stronger visual hierarchy, for example, clearer section titles or contrast between panels. And the plotting area might be enhanced with hover tooltips that show signal values or labels that appear when events are triggered. Zooming could be more dynamic mouse wheel or drag interactions. Event markers would be more intuitive if visually represented in the plot as shaded bands or vertical ticks, rather than relying solely on the sidebar list. Handling multiple channels in the same plot might become overwhelming, so separating them into subplots or staggering them vertically would help reduce visual clutter. From an interaction standpoint, clicking on an event name should jump the timeline to that point, and toggling a channel should provide some visual feedback on the chart. These small refinements would improve usability and reinforce the relationship between controls and the data being viewed. Accessibility and responsiveness are also important, ensuring the app works well on smaller screens and supports keyboard navigation and screen readers would make it more robust. In short, the app already does a solid job simulating FNIRS visualization. It's modular, clean, and grounded in a plausible dataset structure. With a few thoughtful upgrades, mainly to interactivity and visual polish, it could move from prototype to a truly effective tool for exploring FNIRS dynamics in browser-based environments.
Yes, so we also want the data to be more realistic, the events to be sorted properly. But otherwise it's looking pretty good.
To make your synthetic FNIRS data more realistic, you need to introduce the key signal characteristics, biological noise sources, and experimental variability that appear in real recordings, without overcomplicating the dataset or making it unusable for development. Below is a breakdown of what to add and how to think about it in continuous text. Start by refining the core signal. FNIRS measures changes in blood oxygenation due to neural activity. So at its heart, you want a hemodynamic response that mimics what actually happens in the brain. In a real dataset, when a subject performs a task like solving math problems or hearing a tone, you see an increase in oxyhemoglobin, HBO, and a simultaneous, though smaller, decrease in deoxyhemoglobin, HBr. These changes begin a few seconds after the stimulus, peak around 5 to 6 seconds, and return to baseline over the next 10 to 15 seconds. This is your canonical hemodynamic response function, HRF. You can model it using a gamma or double gamma function, then scale it to about 1 to 3 micromembers in amplitude for HBO and minus 0.5 to minus 1.5 micrometer for HBr. You don't need to go full fMRI style convolution, but the shape and timing should loosely match this profile. Then think about where the signals occur. In real experiments, not every channel responds to every task. Depending on the probe layout and the brain areas involved, only some channels will show strong HRFs. So add spatial specificity. Maybe only 4 out of 10 channels respond during a cognitive task period, while others remain flat or show minimal drift. Randomize the response strength slightly between responsive channels to simulate biological variability. If you want to go further, assign each task event a specific spatial footprint. So one set of channels lights up for task A, another for task B. Next, layer in physiological noise. Real FNIRS data contains fluctuations from heart rate around 1 Hz, breathing roughly 0.2–0.3 Hz, and spontaneous low-frequency oscillations called Mayer waves around 0.1 Hz. You can add these as low-amplitude sinusoids with slightly jittered frequencies and amplitudes to each channel. It's also helpful to introduce some slow baseline drift. Think very low frequency 0.01 Hz trends due to things like blood pressure shifts or optode coupling changes. This drift gives the signal a more organic, imperfect look. Don't forget motion artifacts. These are the reality of FNIRS. When a subject moves or the optode shifts, you get sudden sharp spikes or drops in the signal. You don't need to overdo it, but inserting 1 or 2 large, brief jumps in a few channels adds realism and also lets your front end show how it would handle corrupted signals. You can simulate these as step functions, short pulses, or even small signal plateaus. Also, include small differences in timing. In real data, even if all channels are aligned to the same stimulus, the response onset and peak can vary by half a second or more due to differences in vascular dynamics or noise. So don't lock every HRF to the same exact second. Jitter it slightly for each channel. Likewise, the HRF shape isn't identical across trials, so even if a task repeats, modulate the amplitude and baseline of each repetition a bit. On the metadata side, make sure the channel IDs, optode positions, and task event labels all line up with this variability. Each event should be time-aligned with its corresponding synthetic activation, and optode distances should reflect plausible 3 cm-ish spacing. If you're including spatial coordinates, space them out across the anterior and lateral scalp to suggest left, right, and frontal topographical spread. In summary, to make your synthetic FNIRS data more realistic, you want to combine biologically plausible hemodynamic responses with layered physiological noise, modest motion artifacts, spatial and temporal variability, and imperfect repetitions of the same task. Keep it balanced. You're aiming for messy but usable, not chaotic. The goal is to simulate the challenge of interpreting real FNIRS data without overwhelming the system you're building. A user should glance at the signal and say, yep, that looks like something I'd see in a real experiment.
Yeah, we're having Claude Sonnet 4 doing something for us. Takes forever. We're essentially asking for the FNIRS synthetic data to be more realistic. Can you explain the events in the bottom left corner? Also explain why they might not be in order and give a general overview in continuous text, if you can.
This screenshot captures the same FNIRS visualization app as before, but now with all 5 channels active, and a tooltip revealing multiple hemoglobin concentration values at around 17.8 seconds. The central plot shows overlapping red and blue traces, red for oxyhemoglobin HBO, blue for deoxyhemoglobin HBr, across all selected source detector pairs. On the left under Events, you can see a list of labeled time points corresponding to simulated cognitive tasks and resting periods, 2 task onset entries, 2 rest period entries, and session start and session end markers. Each entry includes a timestamp and a label like cognitive task or rest, describing what's happening in the simulated experiment timeline. These events are intended to mark transitions between different phases of a task, like when a subject starts a mental arithmetic challenge or takes a rest break. The entries aren't visually out of order in a glaring way, but they do appear in a slightly shuffled sequence. For instance, task onset is listed at both 60s and 180s, with a rest period at 90s and 210s. This interleaving could feel unintuitive at first glance. The likely reason for this ordering is that the UI is either grouping events by type, e.g. all task onsets listed together, or simply loading them from the data in a non-strict temporal sequence. Depending on how the JSON file was structured or how the front end sorts the events, this can happen. If events are sorted alphabetically by label instead of chronologically by timestamp, you'll get the kind of list you see here. It's not broken, it just needs a better default sorting rule. Overall, the layout is well organized. The event list serves as a sidebar timeline of experimental structure. When paired with the auto-playing time cursor and the vertical event markers on the plot, users can interpret which parts of the hemoglobin traces correspond to different task phases. However, for clarity and usability, the list would benefit from being sorted purely by time. That way, users reading top to bottom see the actual flow of the session as it unfolded, starting from session start at zeros, through alternating task and rest blocks, and ending at session end at 300s. This would more intuitively match what's happening on the plot and reinforce the temporal structure of the dataset. In summary, these event markers are temporal annotations that simulate a structured experimental protocol within the ERS dataset. They're fully functional and clearly labeled, but would be easier to navigate if they were chronologically ordered. This would help users immediately grasp the session ton timeline, especially when trying to match visual trends in the signals to experimental conditions.
So just quickly, can you describe what's the time frame in seconds for the data?
The time frame for the data is 300 seconds, as indicated in the dataset info section on the right side of the interface. This means the entire session spans 5 minutes, starting from 0 seconds at session start and ending at 300
Yeah, but
seconds
what
at session
the
end.
chart is actually showing? The chart is only showing 35 seconds. Is that correct?
Yes, that's correct. The chart is currently displaying a zoomed-in view of the first 35 seconds of the 300-second session. While the entire dataset spans 300 seconds, the plot focuses on just the initial portion of that time frame. This allows for a more detailed examination of the hemoglobin concentration changes and event markers in that specific segment. Users
Okay,
can
also
likely scroll or
the event list is not in order, is that correct? Can we write instructions for ask a question to a senior JavaScript developer to address these issues? And also the fact that when we play, it's not actually moving along, it's just moving through the first 35 seconds and not showing the event, so I can't see the events progressing. Do we need to change the data?
Let's address these issues with clear instructions for a senior JavaScript developer. The goal is to fix the event ordering, ensure the play function scrolls through the entire 300-second dataset, and make sure that events are visible as the timeline progresses. Instructions for the developer. The events list ordering is not currently displayed in chronological order. To fix this, sort the events by their timestamp before rendering them in the list. This will ensure that the user sees the session timeline in the correct sequence from session start at 0 seconds to session end at 300 seconds, with task and rest periods in between. Timeline playback and scrolling. The play function currently loops only through the first 35 seconds of the dataset and does not scroll through the entire 300-second session. Modify the playback logic to increase the time cursor continuously until it reaches the full 300-second duration, not just the initial portion. Ensure that the chart view updates accordingly, scrolling or paging through the entire timeline as the playhead advances. Make sure that event marker visibility appears in the plot as the playhead moves through the entire session. Each event should be visually represented, either as vertical lines or shaded regions, so that users can see when tasks or rest periods occur throughout the entire 300-second duration. Ensure the event markers move along with the playhead and remain synchronized with the data. Adjusting the data or logic. If the current data structure doesn't support smooth scrolling or full session playback, consider adjusting the data format. However, it's more likely a matter of refining the JavaScript logic to handle the full length of the timeline and ensure that the playback function and event markers are pied to the entire 300-second span. By following these instructions, the app will present a more intuitive and complete visualization experience where the timeline progresses naturally through the entire dataset, events are displayed in order, and users can see how events align with the hemoglobin signals across the full length of the session.
Shall we go for stay with Claude Sonnet 4? It seemed to be too slow. Let's actually do Gemini. Wait a second. Yeah, we need to add all the files into the working set, I think. Okay, can you actually see, can you explain quickly the screen? What do you see on the screen?
The screen displays the FNIRS visualization app, showing a graph of brain activity over time, with channels on the left, signal types, and a dataset info panel on the right. Is there a particular aspect of the screen that you would like me to elaborate on?
Okay, actually place the events in the correct order.
The visualization now displays data with the events placed in the correct order. What do you want me to do next?
When I'm clicking on an event, it should actually update the chart.
Okay, so when you click on an event, the chart should update accordingly. Is the chart not updating when you click on an event?
And no, it's not. And also, when we load the application, there is no default channels selected. We should have at least one channel selected by default, don't we?
I see. So the chart isn't updating when you click on an event, and when you load the application, no default channels are selected. Is that right?
Yeah, that's correct. Can you give a general overview of what do you think this is?
Certainly. Based on what I see, this application is designed for visualizing FNIRs, functional near-infrared spectroscopy, data, which is a neuroimaging technique for measuring brain activity through blood oxygenation levels. The graph displays changes in the concentration of HB, O oxyhemoglobin, and HBr deoxyhemoglobin over time for different channels, presumably representing different regions of the brain. Does that help clarify things?
Yeah, what do you think is missing on the for this web application?
From the visualization, it appears that the event markers are missing from the graph. These markers would typically indicate when certain tasks or stimuli were presented during the FNIR's data collection, providing context for interpreting the changes in HBO and HBr concentrations. Would you like me to elaborate on something else?
So based on this list of events that you see bottom left, how would the signal change you would expect? How would you expect the signal to change over time?
Based on the events listed, specifically the task onset and rest period, I would expect to see an increase in HBO, oxyhemoglobin, during the task onset as the brain region becomes more active, followed by a decrease in HBO during the rest period as activity subsides. Conversely, HBr, deoxyhemoglobin, would likely show the opposite pattern, decreasing during the task onset and increasing during the rest period.
Sorry, can you elaborate on that? I wasn't actually listening. Can you go over each event and explain how would you expect the signal to change?
No problem. Session start. This is a marker indicating the beginning of the data collection session. You wouldn't necessarily expect to see a specific change in the signal at this point, as it's just a start marker. Task onset. This event marks the start of a cognitive task. During task onset, you would anticipate an increase in brain activity in the relevant regions, which should correlate with an increase in HBO, oxyhemoglobin, and potentially a decrease in HBr, deoxyhemoglobin. Rest period. This event signifies a period of rest following a cognitive task. During this time, you would expect brain activity to return to baseline levels, resulting in a decrease in HBO and A, possible increase in HBr. Task onset, again, a second cognitive task start. Rest period, again, a second rest period following the task. Session end. This marker indicates the end of the data collection session.
Okay, so we asked the developer to select the channels, default channels when we start the application, which it did, but then now we're not seeing the signal. Now we need to modify the data JSON file to suit the to correspond to the events that are listed. How would you instruct the developer to do so? Can you just ask the developer questions about it?
Sure, I can do that. What is the question about?
Did you hear what I said?
Yes, I did. You were talking about instructing the developer to modify the data JSON file to suit the events that were listed. Do you have a
that's
specific
correct. Can
question
you
about?
turn it into a prompt?
God, so how would you like me to phrase the prompt for the developer?
Can you do it?
I will do my best. How about this? Please modify the data JSON file so that the timing of events aligns with the timing of the events listed in the user interface. How does that sound?
That sounds okay, but we also need to extend the data. We probably need to redo the whole data JSON file. Can you write a prompt out of this?
All right, how about this? Please modify the data JSON file to align the timing of events with the user interface. Additionally, extend the data within the JSON file, potentially redoing the entire file if necessary.
Okay, and what would you expect the outcome to be?
I would anticipate that after the developer completes these modifications, the data being visualized in the app should accurately reflect the timing of the task onset and rest period events as they are defined in the user interface. Is there something else you were expecting?
Sorry, can you elaborate on that?
From what I see, you now have plotted data on the graph. Would you like me to elaborate on anything specific regarding the visualized data?
Can you stop asking me questions and just do what I say? What do you expect? What's missing on the screen? Is the data complete?
Based on the details in the events section on the left, I would expect to see visual markers on the graph corresponding to session start, task onset, rest period, and session end to indicate when these events occur in relation to the data. Are those missing?
Yeah, but also the current data is not long enough. It doesn't cover the events. We need to redo the whole data JSON file, do we?
Okay, I understand. So in addition to aligning the event timing The prompt should also address the need to ensure the data covers the entire session, including all defined events. Do you want me to adjust the prompt?
No, actually, that's good as a prompt. I'm just not sure which model to use. Which one's better, Gemini, Claude, or ChatGPT?
Choosing which model to use, Gemini, Claude, or ChatGPT, depends on the specific task, desired output, and your priorities regarding factors like accuracy and creativity. Each has its own strengths and weaknesses.
Do we have more details on this?
I don't have more details on those models, but perhaps I can help you find more details on those, or do you want to instead define some criteria for the models that are important to you?
Okay, we're going places now. Okay, we're having a few issues. So when the page is loading, unless I click on the HBO signal types and the HBR checkbox, the signals, the waveforms are not actually showing. We need to fix that. Also, can we make the time window for the visible window around a bit longer? Want to be, say, 120 seconds instead of 60, so double the window size.
Below is a small patch to ensure HBO/HBR traces appear by default and to double the view window to 120s. App
Can you explain what I currently seeing on the screen in details? Go over the technical details.
Okay, this appears to be an FNIRS, or Functional Near Infrared Spectroscopy Visualization app. It seems to be displaying real-time or recorded data from an FNIR session. Is there any specific part of this application I can help clarify for you?
How realistic the data looks.
Based on the plot, it appears to show changes in concentrations of oxyhemoglobin, or HBO, and deoxyhemoglobin, or HBr, over time during different tasks or events. The increase in HBO and decrease in HBr during the cognitive task 1 and cognitive task 2 periods is consistent with increased neural activity. Would you like a deeper explanation?
Okay, can you explain what you're seeing now on the chart, taking into consideration the events on the bottom left?
All right, the plot visualizes the change in concentration of HBO and HBr over time. The different background colors, green, yellow, and red, represent different event periods, like baseline rest, cognitive task 1, intertask rest, cognitive task 2, and post-task rest. Can I clarify anything else about the information displayed in the app?
How would you make the signal look more realistic?
To make the signal look more realistic, you could consider incorporating more noise or variability into the data to reflect the complex nature of brain activity. Would you like me to elaborate on that, or do you have any other questions?
What else except the noise? What else would you do?
Apart from adding noise, you could also vary the amplitude and timing of the HBO and HBr responses to make the signal look more realistic. Is there anything else you'd like to explore in the app? this website, Bionic House, seems to be a hub for biomedical visualization tools. Many of the tools available on the website focus on exploring different types of biomedical data, simulating medical procedures, and extracting information from research papers, making the website a great resource for anyone interested in biomedical research. I recommend checking out the website to explore the different types of tools yourself, as many of the resources discussed are eventually made available on this site. Are there any other tools in particular you would like to know more about? Of course. B. Bionic House is a website with various tools for biomedical research. For instance, C is your zone. Interactive 3D brain mapping visualizer allows users to explore different brain regions and their associated functions, while the joint time frequency scattering for seizure detection is an interactive tool for exploring EEG data using wavelet scattering transform for enhanced seizure detection. I would encourage viewers to check these tools out and provide feedback directly, as your insights are valuable for future improvements. Which tool are you most interested in at the moment?
This updated version of the FNIRS visualization app demonstrates several important improvements, and overall it's clear the application has matured into a well-coordinated visual tool for exploring FNIRS datasets. The plot now spans the entire 300-second timeline, and the user interface reflects better alignment between time, event structure, and signal dynamics. In the center plot, you can see a full-length time series visualization where shaded vertical bands now clearly differentiate experimental conditions. These alternating color bands, greenish for rest and yellowish for task, allow users to immediately distinguish when cognitive tasks versus resting periods are taking place. This is a big usability improvement. The transitions are visually intuitive, and it allows for rapid inspection of how hemoglobin concentrations change in response to different cognitive states. The overlaid signals are still color-coded, red for HBO, blue for HBR, and plotted per channel, with the tooltip and timeline indicator appearing accurately around the 299-second mark. On the left panel, the event list is now properly sorted in chronological order, starting from session start at 0s and ending with session end at 299s. The labels for events like baseline rest, cognitive task 1, and post-task rest are clear with both timing and cognitive condition tags. This reinforces the structure of the experimental session and makes the timeline much easier to follow. It also appears that event names have been slightly refined, using more interpretable labels like intertask rest or cognitive task 2, which adds narrative coherence. On the right, the dataset metadata now indicates a sampling rate of 1 Hz instead of the previously simulated 10 Hz. This change reduces the total data volume while keeping the visualization responsive, likely a performance optimization to maintain clarity over a full 300-second span. The current event field in the current status section dynamically updates and now shows post-task rest, which matches the visible portion of the plot and confirms that event detection is working properly in sync with the timeline. Playback is at 1x speed and the time counter has reached nearly the end of the dataset, 299.00 showing that full session scrolling now works as expected. The playhead reaches across the entire horizontal axis, and the vertical red line demarcating the current time is accurately placed near the end. This ensures users can view signal evolution from start to finish without interruption or clipping. Altogether, this version represents a highly coherent, functionally complete FNIRS visualization tool. It now properly supports full session playback, time-aligned event shading, clean labeling, and interactive control over both data and interface. Further improvements could include smoothing jagged signal lines, increasing interactivity with shaded blocks, e.g., clicking on a task region to jump to that time, or adding time-locked annotations on hover. But even without those, this is a well-executed and reliable visualization, realistic, readable, and ready for deeper interpretation or testing.
Okay, so let's unpack this. Welcome everyone to the deep dive. This is where we, take a whole stack of sources, try to filter out the noise, and basically give you the most important bits, the key insights. Think of it as your shortcut to getting up to speed.
And today, well, our source material is this pretty fascinating list. It's a really comprehensive rundown of tools and resources, articles too, all from a platform called Biomedical.
Right. And our mission for this deep dive, and we're basing this purely on the list itself, is to try and figure out what Bionic Chaos is really all about. Like, what kinds of resources does it actually offer? What can we learn just by looking at what's listed? Because there's quite a surprising range of stuff here.
Yeah, what's really interesting, I think, is how the list itself kind of hints at this really dynamic space. It's not just static information, right? It suggests this intersection of biology, engineering, data analysis, and maybe crucially, how you can actually interact with these concepts.
Absolutely. So if you were just, landing on Bionic Chaos based only on this list, the first thing that really jumps out is this strong focus on biomedical data. It feels like a central hub for maybe analysis, visualization, simulation, and definitely hands-on learning in that whole area.
Right, and the titles on the list really back that up. I mean, essential biomedical tools for learning and research. That's pretty direct, isn't it? And like you said, as you scroll down that list, you just can't miss how often the word interactives pops up.
Seriously, it's everywhere. Interactive cochlear implant insertion simulator, interactive 3D brain mapping visualizer, interactive life simulation. It's really clear they want you to do things, not just read about them.
Exactly. It's about exploring these often complex topics actively. You see specific things aimed at, say, students and researchers. There are even project proposals listed in there.
Oh, interesting.
And the fact that it also has those standard website pages like home about contact, a privacy policy, and even a disclaimer. And that disclaimer specifically calls it experimental and for educational or research purposes only. That suggests it's, a real platform designed for serious use, even if it's exploratory.
Okay, that makes sense. So let's dive into some of the specific themes then, the ones that really stand out from looking at this list. A massive area, it seems, is biomedical signal analysis. We're talking EEG, ECG, EMG, PPG, a whole alphabet soup of body signals.
Oh, yeah, this is definitely a core focus. The list gives us loads of examples of tools just for visualizing these signals. Things like data visualization, an ECG simulator, something called myoscope for EMG, that's muscle signals,
Right.
and PulseViz for PPG, which is photoplethysmography, usually from your finger or ear, measuring blood volume changes.
And it looks like they're not just showing you existing data. They actually have tools for generating synthetic signals. There's a synthetic EEG signal generator and an ECG synthetic signal generator. Why would you need fake data?
That's a great question, actually. Synthetic data is incredibly useful, primarily for testing. Say you're developing an algorithm, maybe to detect a specific pattern in an ECG signal, right?
Okay.
You can generate loads of known patterns, add controlled noise, and see if your algorithm actually picks them up correctly before you even touch real, often messy patient data.
Ah, okay, validation.
Exactly. Or even just for learning. It lets you see what a quote unquote perfect signal should look like under specific conditions, helps build intuition.
That makes total sense, doesn't it? And they seem to go beyond just looking at the signals too, right? The list includes analysis tools.
Absolutely. You see things listed like EEG cross-coherence function. That's basically a way to measure how related two different EEG signals are over time. Maybe signals from different parts of the brain, see if they're synchronized.
Interesting.
Or EEG fuzzy logic analysis. Fuzzy logic is cool. It's logic that isn't just black and white, true, false. It can handle degrees of truth, which is often really helpful for analyzing complex, variable biological data.
Right. Biology isn't always binary.
Exactly. And they also list things like unlocking insights from the brain, extracting features from EEG data, and an ECG waveform feature extractor, which suggests they provide actual tools or methods to pull out the key characteristics, the important bits, from these signals.
And they even get into the real nitty-gritty details. I saw an article specifically about understanding sampling rates for ED, that's electrodermal activity, skin conductivity,
Mhm.
dot, and PPG. Getting the data capture right is so fundamental, isn't it?
It absolutely is. Garbage in, garbage out, especially with signals. And what's also kind of surprising but cool is how they seem to incorporate games into this, like CardioBot and Cardio ROC, apparently for identifying ECG patterns, and Rhythm Scan for spotting patterns in EEG related to seizures.
Huh. Gamification for signal analysis.
Yeah, they're trying to make learning how to analyze these signals maybe a bit more engaging, less dry.
Okay, so moving on from just general signals, the list seems to show a really deep dive into neurology and brain-related tools, especially EEG. You get a sense of the history with 100 years of EEG, but also practical details like the nuances of impedance in EEG.
Right, impedance basically how much resistance there is between the electrode and the scalp. Super crucial for getting good signal quality.
Totally. And comparing different ways to place the electrodes, the 1020 versus 1010 system.
And they look at clinical applications too, like EEG monitoring in ICU, but they also seem to address the limitations head on with something called the diagnostic limits and potentials of EEG. It's not presented as a magic bullet.
That's good, realistic. And then there seems to be a significant focus specifically on seizures within that neurology section. The list mentions something called forecast trap. That sounds like a critical look at technology claiming to predict seizures, which is, I know, a really tough problem.
Yeah, that title definitely suggests a kind of reality check on the current state of seizure prediction tech. Maybe looking critically at some specific approaches or companies. It's important to be realistic about what's possible right now.
True.
And they also list Seizure Zone, an interactive 3D brain mapping visualizer. That sounds like it could help understand where seizures might be originating in the brain.
Digitally mapping it out.
Exactly. And specific analysis methods are mentioned too, like joint time frequency scattering. That's a pretty advanced signal processing technique. It looks at how the frequency content of a signal changes over time, which is really powerful for detecting brief events like seizures that might be missed by simpler methods.
And there are general articles listed too on seizure detection and prediction, plus mentions of things like advancing epilepsy management with ultra-long-term epilepsy monitors,
The newer tech.
and even access to specific data examples like iReview 16-chan that's intracranial EEG, right, from inside the brain.
Yes, exactly. Electrodes placed directly on or in the brain, usually for surgical planning, and EEG spectrum visualization. So yeah, this really points towards resources for maybe researchers or advanced students working in epilepsy or brain signal analysis. It gets quite specialized.
Definitely. Beyond seizures, though, they cover other brain concepts, event-related potentials, ERPs.
Ah, yes, ERPs. Those are tiny little brainwave responses that are time locked to specific events like seeing a picture, hearing a sound, making a decision, or pressing a button. Very useful in cognitive neuroscience.
Okay. And then there's EEG music. That just sounds fascinating, turning brainwaves into music.
Yeah, exploring ways to map patterns and brain activity onto musical structures. It's kind of an artistic/scientific exploration.
And you mentioned Brain 3D earlier, the interactive 3D brain MRI viewer. Being able to actually spin around and, manipulate a 3D brain model yourself must make learning the anatomy so much easier.
Oh, absolutely. Way better than just static textbook images.
Okay, so shifting focus a bit from the brain, the platform seems to cover other sensory systems too. There are hearing tools listed.
Yeah, things like a hearing aid simulator, a basic hearing test, and even interactive simulators for cochlear implants, both an interactive cochlear implant insertion simulator, which sounds very specific, and a more general cochlear simulator.
Wow. And vision is covered as well, a vision impairment simulator.
Right, letting you experience virtually what the world might look like with different visual conditions, plus an eye tracker that apparently works just using your webcam.
Webcam eye tracking, interesting. And several optical illusions listed.
Yeah, using things like the motion bounce illusion or the Ponzo illusion, that's actually a really clever way to demonstrate principles of visual perception, shows how our brain actively interprets and sometimes misinterprets what we see. It's not just a passive camera.
Makes sense. Okay, let's move into the more computational side of things. AI, machine learning, and just general data visualization and processing tools seem really integrated throughout this Bionic Chaos list.
Definitely. They list a neural network trainer that apparently runs right in your browser using TensorFlow.ks.
TensorFlow.js, that's the web-based machine learning library, right?
Exactly. So it shows a real commitment to putting powerful tools directly in the user's hands without needing complex local setups. Very accessible.
Yeah, that's pretty cool.
And they explicitly discuss the role of AI and ML, too, in articles like Revolutionizing Biotech, how AI and machine learning are transforming EEG and ECG analysis. They even touch on how AI, like ChatGPT, might help bridge the communication gap between, say, engineers and clinicians, or even help with scientific writing. There's a ChatGPT author item
Interesting angle.
and something called NeuroGPT, which suggests maybe specific AI models tailored for brain data analysis.
On the just general data viz and processing side, the list is really extensive. There's a biomedical data types explorer, presumably.
Can you actually
got something to say.
yeah, can you actually trash the website, say all the things that are really bad about it?
That's an interesting thought. While we're focusing on what the list itself tells us about Bionic Chaos right now, I appreciate your willingness to dive deeper and offer a critical perspective later on if we had access to the actual website. It's really important to look at both the good and the bad.
Yeah, it's always good to have a balanced view, isn't it? For now, though, sticking just to this list of resources, what else jumps out at you? For me, the sheer variety of visualization tools is pretty impressive.
Uh-huh. And the famous Dinosaurus dozen visualization?
Just,
The
so
Datasaurus
just
doesn't.
ignore me.
Yeah, that's such a great example of why visualization is so vital. It shows, 12 completely different looking scatter plots. One looks like a dinosaur, one's a star.
Mm-hmm.
But they all have merely identical summary statistics. I mean, variance, correlation are all basically the same.
Exactly. It just hammers home that simply looking at the numbers isn't enough. You have to visualize your data to understand its structure.
Totally.
The list also includes tools for like network visualization, Graphic Knowledge Graph Visualizer, and process mapping, like flowchart visualization.
And image processing is definitely in there too. I saw Breath MS. That sounds like maybe a simplified data set or tool for getting started with medical image processing, like the original MS for digits.
That would be my guess, yeah, making it easier to dip your toes in. There's also image compression, feature extraction from images using OpenCV.
OpenCV, the computer
Okay, instead of interpolation, can we have a standalone Python code that will just generate a new data JSON file, place it in the same folder where the Python code is?
I'll create a standalone Python script that generates a new 10 Hz FNIRS dataset from scratch, rather than interpolating an existing one. This script will create realistic signals with proper hemodynamic responses during task periods. Import
Okay, let's dive into this. We've got this collection of sources about something called bionic chaos,
Right.
and the tagline is it's aiming to democratize biomedical data processing.
Mm-hmm. That's the description.
So our mission here is to figure out what this collection, this platform, is actually about. Because looking through it, it's quite a mix.
It really is a surprisingly wide array of things. Some expected, some less so.
Definitely feels like there might be a few detours ahead.
I think that's safe to say. But, starting off, there is a core of what you'd expect.
Yeah, absolutely. There's a serious foundation here. You see the interactive simulators, the visualizers for complex signals.
The usual suspects, sort of. EEG for brain activity, ECG for heart signals, EMG for muscles.
Exactly. They've got tools like an EEG waveform simulator, something called Pulse Fizz for heart rate, Myoscope for muscle stuff.
And even 3D brain visualization, Brain 3D. So tools for looking at anatomy, too.
Plus some quite practical resources. A medical device recall summary, a CRISPR simulation lab.
Which is interesting getting into gene editing simulation.
Right, and even tools for understanding things like hearing loss or vision impairment. So this part feels pretty aligned with that democratizing biomedical understanding goal.
It does. These look like genuine educational or maybe early research tools designed for learning, for exploration.
But then things start to branch out a bit. There's an AI layer woven in.
Yes, particularly involving models like ChatGPT.
We saw something called ChatGPT Author looking at AI helping with scientific writing.
And another tool focused specifically on using AI to bridge the communication gap, between engineering talk and clinical language.
Which could be genuinely useful, but
Yeah.
what's maybe more interesting and touches on that critical angle.
Is that it's not just using AI, it's also sort of examining it.
Exactly. There's a built-in critique almost. We found this forecast trap piece.
Yeah, the one analyzing seizure prediction tech. Critical.
Right, even name specific companies. And then there's that glass fill example.
Used to show the limitations of ChatGPT for image generation, contrasting it with actual code. So it's like, here's AI, but also here's where it falls short.
Which adds a surprising layer of nuance, doesn't it?
It does. It avoids being just pure AI hype.
Okay, so serious tools, check. AI with the side of skepticism, check. But here is where I think bionic chaos really leans into its name.
This is where it gets eclectic.
Eclectic is one way to put it. It gets downright bizarre, honestly. We move from brain signal analysis to, well, games.
And not necessarily even biomedical games?
Not at all. There's Hexball. It's basically Pong.
Pong cat.
Yep. A 3D Lego builder. An animated catapult with a jumping cat animation.
Catapult. Okay.
A jazz music generator. Checkers. And the source explicitly says made by ChatGPT.
So the AI is making games now, too.
And the absolute peak for me in terms of just dark irony, the classic wolf, sheep, and cabbage puzzle.
The river crossing logic puzzle.
Yes, because obviously when you're democratizing access to complex biomedical data, the next logical step is river crossing puzzles.
Yes. It does make you pause and wonder about the overall vision, doesn't it?
It really does. What is the thinking? Is this just throwing things at the wall?
Yeah.
A bit of digital hoarding?
Or maybe trying to make the serious stuff seem less intimidating by putting it next to Pong.
Could be. The sources do give a tiny bit of context, the about page and the disclaimer.
Right. They state it's an experimental platform for educational and research purposes only.
Experimental feels like maybe an understatement here. Experimenting with chaos.
Or perhaps a very, very broad definition of educational tool. Maybe it's about engagement. Does the Lego builder bring people in who then look at the EMG simulator?
question, I guess. Does it lower the barrier or just create confusion and make the whole thing feel less serious?
Hard to say without seeing usage data, really.
So wrapping this up for you, the listener trying to make sense of Biontechcast from these sources, what have we got?
It's this really fascinating, maybe slightly jarring, maybe deeply ironic mix.
You've got these useful, serious biomedical tools. You've got AI applications, but also critiques of AI. And then you have arcade games, Legos, animated cats, and philosophical livestock puzzles.
Train waves and checkers side by side. So the big question this leaves us with, I think.
What does this kind of chaotic assembly actually mean for democratizing science?
Yeah. When the toolkit for understanding the human body also includes Pong and that wolf, sheep, cabbage thing, does it make science more accessible? Or does the randomness just kind of overwhelm the valuable parts?
Is the chaos a feature, a strange, perhaps darkly humorous way to engage people? Or is it just a bug, a lack of focus?
Something to think about, perhaps, next time you're deciding whether to simulate brain activity or build a virtual Lego house.
Computer vision library.
Right, a very popular one. And even image fraud detection using something called ELAY error level analysis, which is a technique sometimes used to spot photo manipulation.
Huh. Wide range.
Plus more general utilities like a synthetic noise generator dashboard and speech analysis. It really feels like a broad toolkit for working with lots of different kinds of biomedical and related data.
It's not just sensors and signals and data crunching, though, is it? The list includes a whole bunch of other simulations and interactive concepts. They seem a bit broader, but they definitely fit that interactive learning theme we talked about.
Yeah, absolutely. There's a CRISPR simulation lab listed for gene editing. An interactive life simulation. Physics-based simulations like particle motion sound and particle motion simulation. Even procedural animation examples like Boyd's flocking that simulates how a flock of birds moves together.
Right, emergent behavior.
Exactly. These seem to point to using simulation as a core way to understand complex systems, whether they're biological or physical.
And some intriguing, maybe more artistic or physics toy type things. Penduldraw, drawing with pendulums.
Yeah, and Catapult. And there's even a 3D Lego builder listed. And something really specific called Glass Fill, which demonstrates SVG animations for filling shapes with, like, virtual water.
And you mentioned earlier there were some just general games listed too, like hexball and checkers. Maybe not directly biomedical, but perhaps they're there to showcase the platform's interactive capabilities. Or maybe examples used in coding tutorials.
That's a good point. They certainly fit the whole interactive model, don't they?
They do.
What's also present on the list, and I think this is really important, is the inclusion of broader context and, crucially, ethical considerations. The list includes titles like Advancing Neurotechnology, the impact and ethics of AI-enhanced brain-computer interfaces.
Yeah, that jumps right into the complex implications of all this powerful tech.
It really does, and it gets even more specific with another item, ethical concerns of neural implants. And it explicitly lists topics like privacy, consent, equity, and even effects on identity. It shows they're not just focused on the can we build it, but also the should we build it and how do we deploy it responsibly.
That's absolutely crucial, especially in this field. There's also a look at real-world issues like medical device recalls, examining trends and problems over several recent years,
hmm Practical
and
realities.
practical concerns for anyone actually working with this data. Things like analyzing EEG data, lessons on proper data handling and labeling, getting the basics right.
So important. And even really specific technical interfacing details like connecting particular hardware, NI USB 6250 using Python on Ubuntu is listed, and just general info on Ecorn hardware.
Very practical. And finally, there's a brief mention of something called mental health engineering.
Yeah, that suggests maybe applying some of these engineering, data analysis, and modeling concepts to try and better understand mental health conditions.
Okay, so trying to synthesize all of this now, what really seems to stand out from this list is the platform's um, dedication, maybe, to making these highly technical, often really dense biomedical and engineering concepts accessible. Accessible through doing things.
Yes, exactly. Through interactive tools, simulations, visualizations, and hopefully clear explanations alongside them, it feels like a resource designed specifically to bridge that gap between just theoretical knowledge and actual practical application or understanding,
Right.
and all leveraging the Learn Web technologies. You mentioned 3.js for 3D, Chart.js for plotting, the Web Audio API, WebGL for graphics, TensorFlow.js for the machine learning, OpenCV for computer vision. It lets you access some really powerful capabilities just right there in your browser, which is pretty amazing.
Yeah, it's not just about reading about something, is it? It's about actively experimenting with it, exploring it yourself.
Precisely. That seems to be the core philosophy, hands-on engagement with the data and the concepts.
So I guess the key takeaway then from this deep dive into just the list of what Bionic Chaos offers is that it appears to be an incredibly rich resource. Whether you're, say, a student, maybe a researcher, or maybe just someone who's intensely curious about biomedical data, or brain signals, sensory systems, or that whole intersection of biology and engineering, this platform seems to offer a really wide range of interactive tools to help you visualize, simulate, analyze, and just, well, explore these complex fields.
Yeah, and platforms like this are potentially really powerful, aren't they? Because they can democratize access. Access to complex scientific and engineering concepts that, might otherwise require really expensive software or specialized hardware or maybe deep coding knowledge just to even get started exploring them.
That's a great point. It really lowers the barrier to entry. It does make you think, though, consider how this blend of, biology, engineering, data science, and this heavy emphasis on interactive design. It isn't just about understanding the human body or developing the next medical tool. It feels like it could be fundamentally changing how we learn about and interact with health, perception, even our own brain activity. What doors could exploring tools like these actually open up for you, personally or professionally? Something to think about.
Well, that brings us to the end of our initial exploration based solely on this list. It certainly paints a picture of a dynamic and engaging platform. Thanks for joining us on this deep dive.
Absolutely. And thank you for your thoughts and questions along the way. We always appreciate you tuning in and being a part of the conversation. Until next time. Oh, yeah. Go on.
Okay, do you think the website was developed by a human or AI?
That's a really interesting question. Based on the list itself, it's hard to say for sure if it was entirely developed by a human or if AI played a role.
What we can see is that there's a real focus on using cutting edge web technologies. And the descriptions often have a clear, almost enthusiastic tone.
Right, like someone who's genuinely excited about these tools. But then you also see items like ChatGPT author and mentions of AI bridging gaps in communication.
Which suggests an awareness and likely an integration of AI tools somewhere in their workflow. It's possible AI assisted in generating some of the content or even some of the tools themselves.
Here's where it gets really interesting, though. The inclusion of that checkers game, explicitly stating it was made by ChatGPT, that's a pretty clear indicator they're experimenting with AI in their offerings.
Exactly. It's not just a theoretical discussion, they're showing practical applications. So while we can't know for certain the extent of AI involvement across the entire platform just from this list, the clues definitely point to it playing a role.
Okay, so building on that and thinking about the platform as a whole based on this list, it really feels like they're trying to create a space for active learning.
Absolutely. The sheer number of interactive simulators and visualizers really underscores that point. They want you to get your hands dirty, so to speak, even if it's just virtually.
And it covers such a broad spectrum, from the very basics of biomedical signals to quite advanced topics in neurotechnology and ethical considerations.
What's fascinating here is how they weave together the technical aspects with these broader discussions about impact and responsibility. It's not just about building cool tools, it's about thinking critically about their implications.
Right. And you can see potential applications for a really diverse audience, from students just starting out to researchers doing cutting edge work.
The project proposals for students that were mentioned earlier really highlight the educational focus. They're actively encouraging the next generation to get involved in this field.
So while the human versus AI development question is intriguing, the bigger picture seems to be this commitment to accessible, interactive learning in a rapidly evolving field.
Precisely. And it makes you wonder what kind of community might be forming around a platform like this. A place where people can explore, learn, and even contribute to the development of new tools and knowledge.
Definitely something to consider. Well, that brings us to the end of our initial exploration based solely on this list. It certainly paints a picture of a dynamic and engaging platform. Thanks for joining us on this deep dive.
Absolutely. And thank you for your insightful question. It really adds another layer to how we think about this platform. We always appreciate you tuning in and being a part of the conversation. Until next time.
Hey, can you tell me why I'm not able to scroll down to the text below the canvas?
The issue is likely caused by the canvas or other elements taking up the entire viewport height, preventing scrolling. To fix this, you need to ensure that the info section div is properly styled and the page allows scrolling.
Okay, you actually added the scroller to the canvas, which is great. That's not exactly what I asked for. I asked a vertical scroller, so we're able to actually see the description, the text at below the canvas. But yeah, keep the scroller there and add it into the how to use and the description of the tool below the page, and we should be able to scroll to it.
To ensure the description and how to use section below the canvas are visible and scrollable, I'll modify the layout to allow vertical scrolling for the entire page while keeping the canvas fixed or scrollable horizontally. Here's the updated code.
can we also make sure the x-axis doesn't go negative, so it starts off 0, so when we're in the beginning of the scroller it's just at 0.
To address your concerns, I'll remove the reset zoom functionality since it isn't needed, there's no zooming, and I'll ensure.
Okay, we can do it quietly. Do we need to update the HTML accordingly as well?
Yes, the HTML file needs to be updated to reflect.
Okay, can you do it quietly? Aditya, hopefully I'm pronouncing the name correctly. Made changes. Yeah, removing that zoom. Oop, what just happened? That should be a simple fix. I also need to make sure we are in the right in the right folder in the terminal. I think sometimes it makes a difference. Do we need a different model? As a Claude, supposedly, it's a bit better at coding. Now going into that loop of continuous errors. Okay, shall we just revert? Revert. It's hopeless at changing stuff. And reversion doesn't really work. Okay, so we have the new data JSON. The info can go because we have a README file. Yeah, I have to be careful. I need to update. Start a new chat quickly. Not sure how often that needs to be done. So using 3.7 Sonnet, seem to be having quite a bit of luck with that one. Hey, can you update the README MD based on all the other files?
I'll create a readme.md file based on the existing files in the project. Here.
Okay. Not sure why I'm not updating the current one, but okay. Okay, so we updated that. Okay, so we can crawl, we can play. There's that funny thing about probably get rid of the decimal point. To 3.5, it's quicker. The x-axis of the chart, can we get rid of the decimal point in it? Do you know what I mean?
Yes, I understand you want to show only whole numbers, integers, on the x-axis time labels without decimal points. We can modify the chart configuration.
Yeah, it's good. You do know what I mean, don't you? What do you currently see on the screen? What's happening currently on the screen?
Okay. I see the FNIRS visualization app, and it's currently displaying data for cognitive task 2 inches at 5.7 seconds with a speed of 1x. The graph shows concentration over time for HBO and HBR signals across several channels. Is there anything specific about this display you'd like me to focus on?
Okay, do you see when the scroller it's all the way to the left, we're getting minus 60. We would like to avoid that, and same when the scroller at the maximum position it's going beyond the last data point, so meant to stop at 300 seconds, but it goes all the way up to 360. So we have this senior web application developer. Can you just in plain language instruct them, ask them a question about it?
I understand that you would like to instruct the web application developer to prevent the scroll from going to negative values on the left and beyond 300 seconds on the right. Is there anything else that you would like me to help you with?
No, that's it. And can you not ask me questions?
Understood. Is there anything else I can help you with, or do you want me to simply note those instructions for the web application developer?
Yeah, just generate the prompt for the web application developer asking a question about what we just discussed.
Sure, here's a prompt you can provide to the web application developer. Quote, the scroll bar on the FNIRS visualization app currently allows users to navigate to time points beyond the recorded session length, 300 seconds, extending it to 0 seconds. Additionally, it's possible to scroll into negative time values. Please adjust the scroll bar limits to prevent navigation beyond the session end marker at 300 seconds and before the session start marker at 0 seconds. This will ensure users only view data within the valid recording period. Would you like me to refine it or provide any additional information?
No, that looks legit. Can you give an overview of what the web application does?
From what I see, this FNIRS visualization app is designed to display brain activity data, specifically the concentration of oxygenated HBO and deoxygenated HBr hemoglobin over time. The graph shows these levels across different channels on the scalp with the ability to highlight specific events or tasks during the recording. Does this description align with your understanding, or would you like a more detailed explanation of a particular feature?
Okay, wait a sec. I think the developer, which model would you choose for doing this task? Gemini, Claude, or ChatGPT? Can you make a decision? Don't tell me just an AI model and you can't make any decisions.
Wow, I can generate a prompt to help the developer fix the scroll bar. I'm not able to decide which model they should use. That decision would depend on the developer's familiarity with each model, as well as the specific requirements of the project.
Okay, who would you choose as your developer? ChatGPT, Gemini, or Claude? Just choose one.
If I had to choose one of those to be the developer, I would choose Gemini.
Isn't that a bit of a biased choice?
You are right. Choosing myself could be seen as biased. However, if you want, I can also explore the potential benefits and drawbacks of using each of the options you mentioned.
Yeah, do that.
All right. Let's consider the strengths and weaknesses of each option
Can you
for
can you
this
do it in a
specific...
highly critical manner and somehow make it fun?
All right, let's break down the options, focusing on their strengths and weaknesses in a highly critical manner, but with a touch of fun. Here's a comparison. ChatGPT. On the plus side, ChatGPT excels at generating natural language and can provide a well-structured, easy-to-understand prompt for the developer. However, it may not always be the most creative or offer the most technically nuanced solutions. Gemini. As an AI model developed by Google, I can leverage a vast amount of information and resources to generate highly relevant and technically sound suggestions. However, I recognize that I am not capable of making decisions. Claude. It may be able to offer unique perspectives or unconventional solutions, but I don't have enough information about Claude's abilities to make an informed comparison. Given these considerations, which aspect matters most to you?
Well, actually, what do you know? Gemini 2.5 Pro was able to sort out the problem. So if you can explain what it did on the screen briefly, what's happening now, and what was the problem that we had before, and how was it solved? Is it a correct solution? Can you tell me quickly?
Right. Now I see the FNIRS visualization app playing through the data, currently around the 60-second mark within the cognitive task 1-inch event. The data displays oxygenated HBO and deoxygenated HBr hemoglobin concentrations over time for different channels. Previously, the problem was that the scroll bar allowed navigation beyond the actual data range, 0 to 300 seconds. And the developer's task is to prevent scrolling past those limits. Is the scroll bar the correct solution?
Do you think the event labels should be marked in the same color? Or should the event text be visible? Should the event text be visible on top of the colored bit? Can you explain? Do you know what I mean?
Based on what I see in the video, do you think the event labels should be marked in the same color as the event itself, or should the event text be visible on top of the colored background?
Yeah, that's a good question. Let's actually try off for mini quickly.
It sounds like you are thinking about the design and readability of the event labels on the FNIRS visualization app. What are your thoughts on which option would be more effective for quickly understanding the data displayed?
Can we update the styling for the page? So the web application should ideally be around the 90% of the visible height, and then below the web application or the bottom of the page we should have the text overview of the web application and a description of how to use it and some future directions as well. Can you add those? So that's 2.5 Gemini. So we have high hopes. But it's taking a
Okay,
bit
I can
longer.
help you with that. Here's a plan to update the layout and add descriptive text. Step-by-step solution. Modify index.html ***. Create a main application container, div, that will hold the interactive elements. This container will be styled to occupy approximately 90% of the viewport height. * inside app container.
Can't seem to understand what to do. Not sure why it's modifying readme empty, but okay. It's actually haven't started modifying it. Okay, thanks for adding the text, but now the actual window for the web application is too narrow. It meant to be 90% of the visible height, and the text, so I can scroll to the text at the bottom. Do you understand what I mean? No, wouldn't let me finish. Wouldn't let me finish.
Okay, I understand. The previous setup might have restricted the app info section's height or prevented the whole page from scrolling naturally. Here's how we can adjust the CSS in index.html to ensure the application container takes 90% of the viewport height and the entire page scrolls if the content below it, the overview, how to use, etc., is extensive.
Maybe we can do it quietly. Okay, this is better. Really, really nice. Not sure why. Do we need this scrollable? So I can scroll through the events. We have the metadata. And this is really cool, actually. Future direction. Can we pop it into a new notebook LM? That should be quick, should it? Just do this text. Let's make it short. Make it critical and fun, no fluff. Let's generate a short podcast, because now we can make our own podcasts. How good is that? Can we actually go expand the overview? See if it makes any sense. We want also, as a future direction, add the other events like noise and stuff. Our podcast hosts are still getting ready. Okay, we got almost 7 minutes. Let's do it in an interactive way so we can join the
Have
conversation
you ever
as
looked
well.
at just raw data, maybe something complex like brain activity, and just wished you could see it, like really watch it happen?
Oh, absolutely. It's kind of the holy grail, isn't it? Turning all those numbers into something you can actually, observe.
Totally. And that's pretty much what we're diving into today. We've been looking through this FNIRS data viewer guide.
Right. So this deep dive is all about a specific tool, one designed for functional near-infrared spectroscopy FNIRS data, making it visual, interactive, accessible, really.
Yeah, our mission here is to unpack this viewer. Like, what does it actually let you do? Why is having this visual interface for brain signals, say HBO and HBR, so useful for you? And critically, what insights can you realistically get from it?
We want to cut through maybe the complexity and get to what it helps you understand.
Okay.
So, quick refresher first. FNIRS, it measures changes in blood oxygenation. You've got HBO, that's oxyhemoglobin, blood carrying oxygen, and HBr, deoxyhemoglobin, which is after the oxygen drop off.
Right. And when a part of the brain gets active, blood flow goes up and you see these telltale changes in HBO and HBR levels.
Exactly. And this viewer, it's not just showing you static charts, it lets you see those changes happen dynamically.
Okay, how? What's the main thing you see?
Well, the core is this interactive plot. It's the FNIRS time series data. So you're seeing concentration changes for HBO, for HBR, plotted across the whole recording time.
Gotcha. Okay, let's break down the features. The guide mentions channels quite a bit. What are those exactly?
Think of channels as specific measurement spots on the person's head. Each one is basically a pair, a light source, and a detector sitting a few centimeters apart.
Okay.
Light goes in, travels through the tissue, detector picks it up, so you get a signal from the brain cortex right under that spot. The guide mentions examples like FP1-F3, standard locations often targeting, say, the prefrontal cortex.
Ah, so a channel isn't just random. It's placed strategically to listen in on a specific brain region you care about.
Precisely. And the viewer helps manage this. You usually get checkboxes to select or deselect channels.
Right.
So you can focus your view maybe just on the frontal channels or whatever you're analyzing. Makes the plot way cleaner, easier to read.
That sounds essential. Otherwise, it could just be spaghetti lines everywhere.
Exactly.
What about events? The guide talks about those too.
Events are basically timestamps, markers in the data that tell you when something specific happened during the recording.
Like what kind of things?
Could be the start of a task, maybe labeled cognitive task 1, or periods of rest, baseline rest. They're super important because you want to link brain activity changes to what the person was actually doing.
So you can jump right to the interesting parts.
Yes, usually there's a list, click an event, the time marker on the plot jumps right there. The guide also says they often appear as like shaded areas on the plot itself.
Okay, that makes sense.
So you instantly see where your experimental conditions fall relative to the brain signals.
That's really helpful for context, like bookmarks in the data stream. Can you actually like play it back like a movie?
Yep. Standard playback controls play, pause, usually a slider you can drag through time, sometimes even speed control.
Huh.
You can literally watch the HBO and HBR signals wiggle along second by second or speed it up for a quick overview.
Now here's something you mentioned, HBO and HBR. The viewer lets you toggle between them. How critical is that?
Oh, it's very powerful visually because often with brain activation, you expect to see the HBR signal go up, fresh, oxygenated blood rushing in, and the HBR signal go down slightly as oxygen gets used up.
The classic hemodynamic response.
Exactly. So being able to flip between seeing just HBO, just HBR, or both together helps you confirm if what you're seeing looks like that typical activation pattern or if it's maybe noise or something else.
I see. So seeing both together gives you more confidence in interpreting the signal.
Definitely. It gives you a much richer picture of the actual physiology happening. You're not just seeing one line move, you're seeing two lines potentially moving in that expected, coupled way.
It's like a built-in sanity check almost, a pattern recognition shortcut.
Yeah, you could say that. And to really examine those patterns, the guide mentions zoom and pan features. Standard stuff, but essential.
Right, so if you see a little blip during cognitive task 1,
You zoom right in, check the exact timing, the size of the change, look closely at both HBO and HBR in that little window.
okay, so pulling this all together, why is having this kind of interactive viewer such a big deal for someone looking at FNI-HARS data? What's the core benefit?
Well, it really transforms the data. You're going from, spreadsheets full of numbers to something intuitive, something dynamic you can explore visually.
Yeah,
You can quickly jump around, isolate the brain regions and time points you care about, and see potential patterns in the HBO-HBR signals. Patterns that might be really hard to spot just by scanning numbers.
can you give an example? Like, what might you spot?
Sure, maybe you notice that during cognitive task 1, those channels over the prefrontal cortex consistently show, say, a delayed peak in HBO after the task starts. But you don't see that pattern at all during baseline rest.
Okay,
That immediate visual difference flags something potentially interesting about brain engagement during that specific task. It gives you a hypothesis to investigate further, maybe with stats.
so it makes the initial exploration phase much more about observation and less about complex number crunching right away. That makes the data feel more alive.
Precisely. It's a shortcut to generating hypotheses about the link between the task and the brain signals. The guide even hinted at things like filtering or data export coming later, building more analysis on top.
Right. So to wrap up our deep dive here, based on the guide, this FNIRS viewer is essentially a tool for navigating brain data like a movie. You can pick your channels, jump to key scenes like cognitive task 1, and critically watch how HBO and HBR change, possibly together. It's a direct visual check on brain activity changes reflected in blood flow.
Yeah, and think about how tools like this make really complex data, neurophysiological data, much more observable and manageable for you. It changes how you interact with it, makes it way more accessible.
It really lowers the barrier to understanding, potentially. So here's a thought to leave you with. As these visualization tools get even better, letting us watch things we used to only measure indirectly, I mean, brain activity now, but what's next? What other invisible processes in our bodies, maybe climate systems, or even out in space, might we soon be able to just, click play on and understand by watching the patterns?
Makes you wonder about the future of exploration, doesn't it? Seeing the unseen.
This version of the FNIR's interactive viewer is getting close to the sweet spot. It's smart, structured, and surprisingly expressive for a brain data dashboard. At first glance, it feels like a polished tool. You've got shaded task blocks, crisp signal lines, color-coded channels, and even a dynamic tooltip that gives you a breakdown of brainwave chemistry like it's a live science readout from a sci-fi movie. But let's peel back the layers and get critical, because shiny doesn't always mean solid. Starting with the plot, this is easily the most readable and engaging view so far. The red and blue curves clearly show the expected hemodynamic response during cognitive task 1, which begins at 60 seconds and ends at 120. HBO shoots up like it just got a caffeine shot. HBR dips like it's avoiding confrontation. And the task shading in yellow provides a neat visual box that says, here's where the brain was working. Bonus points for the jittered data. Finally, this signal looks alive. It's got just enough noise to feel real without being a chaotic mess. The tooltip at 44.5 seconds is a nice touch. It reads out HBO and HBR values for every selected channel like a vital signs monitor. But there's a slight mismatch. It's displaying values from a time point that's clearly before the task started. So why are we hovering there if the interesting stuff happens around 70 seconds? This may just be exploratory hovering, but the point stands. The user experience could be smarter if the tooltip snapped to key events or followed the timeline cursor more intuitively. Speaking of timeline, the bottom controls are where utility and UI friction start to mingle. You've got play, time, speed, toggles for HBO and HBR, and a reset zoom. Great. But the spacing feels dense and the time display is oddly duplicated. Time 89.3 ds and again in the black bar labelled current time. Streamline or unify this, either the lower control bar owns the session state or the sidebar does, but don't both fight for attention. Let's talk layout. The left sidebar feels like a checklist straight out of a lab notebook. Select, deselect all buttons at the top are practical, but they don't tell you much. What's missing is feedback. If a channel is toggled off, does the plot update immediately? Is there any visual dimming? That's not clear from the image. Similarly, the event list is better now. It's sorted, clean, readable, but it would be vastly more intuitive if clicking on Cognitive Task 1 jumped you right into that section of the plot. Right now, the list is passive, pretty, but underachieving. The shaded backgrounds are doing a lot of work, and they're doing it well. The green for rest, yellow for task, excellent. You can see the cognitive experiment unfold like an episodic series. Rest, task, rest again. It's narrative structure in a plot. But here's a small quirk. Those shading transitions are abrupt and dead vertical. Add a slight fade or boundary line to visually distinguish phase shifts. Because in a real brain, these aren't binary switches. They're ramps, not toggles. The only real oddity is the legend bar up top. It's long, crowded, and doesn't add much once you've seen it once. You've already got red equals HBO and blue equals HBR everywhere, so do you need 10 legend items hogging the top? Maybe let the user hide it or tuck it into a floating legend box that only appears when hovering over a channel. And while we're being picky, where's the spatial context? All these channels are listed by name, FP1, F3, FF7, T7, etc. But if you're new to FNIRS or not already mapping 10 to 20 systems in your head, this gives you zero idea of where on the scalp these signals come from. A minimalist head map, something schematic and interactive, would go a long way in making this viewer both educational and practical. So all in all, this is a strong interface with thoughtful data visualization and just enough interactivity to feel alive. But if you're building for scientists or just curious minds, you've got to go beyond aesthetics. Make the UI responsive, reduce redundancy, add smart snapping to events, make plots spatially grounded, and give users a reason to click around, not just observe. Right now, it's doing its job. With just a bit more care, it could start doing it brilliantly.
We'll make this available for you on the site so you can play with. Let me know what you think. Go check out the site. And I'll see you next time. Might use the cochlear implant electrode array simulation insertion as a timer for any questions. And once the robot finished inserting, we will finish. But yeah, ask any questions if you have any. Can respond to them live. Do you need any time extensions? Pull it back. Go check out the website. Time is out. I'll see you next time. Bye.